Hello, everyone. In this video, I will be going over the latent variable actor-partner interdependence model and estimating that model within R, specifically the lavaan package. So we can go ahead and we can get started simply by talking about what packages we will be using. So I'm using the Haven package to bring in my SPSS data file. I'm using lavaan to run our analyses. We actually won't be creating any diagrams, but then if you wanted to, you could use the lavaan plot uh, package. And then the SBS diff package estimates the scaled chi-square difference test for the Satora-Bentler and Yuan-Bentler corrections, which we will be using. All right, so first we will create our data object. And so this is my SPSS file. And so I'm going to create my data frame, I should say. Um, and then we'll move into creating our model. And so I'm just calling it latent APIM, and you will see throughout the video that I have very uncreative names for my models. I would encourage you all to use more creative names, but I will be just doing latent APIM 1, 2, 3, 4, etc., etc. So in the observed variable actor-partner interdependence model, we typically take a mean or we typically take a sum of a bunch of different items. And so, although that is a really easy process and, it takes, all of 30 seconds in a lot of programs, one of the problems with using sum scores or using mean scores is that there's measurement error baked into those scores. And so, one of the benefits of using a latent variable is it is able to effectively model that error, that measurement error. And so, one of the consequences of being able to do that is that you're actually going to get more precise parameter estimates. So, when you have measurement error from a sum score, your parameter estimates are going to be either too big or too small. And most often, it's going to be too small. Um, and what that does is that reduces the amount of statistical power that you have. And so that is, of a great consequence, particularly if you have a smaller study and you're kind of hovering right around that power of 0.80. Or perhaps you're even underpowered. And so, having a more accurate parameter estimate's actually going to be potentially even more impactful. So if you have a smaller sample size already, and then you throw modeling measurement error on top of that, you're going to have even fewer participants than you actually think you have. So for example, if you have 150 dyads, but you're using measurement error, you really might only have the power of 125. Again, I'm kind of creating some arbitrary numbers here. So you only have the ability to estimate the effect size for accurately at the population level for, again, now those 125 dyads. So again, this is going to be really, really important to the accuracy of your parameter estimates. And so the first thing that we're going to do is specify those latent variables. All right, so that's what this code is. And so for those of you who are kind of newer to latent variables are, it's the idea that there is a process that we believe to exist, but we don't have it in our data set. And most of the social and behavioral sciences is going to be based on the idea of latent variables. So we probably believe in depression, for example, but we can't throw people in an MRI machine and see depression. We can't just look at someone and to say, oh, they're depressed. We can't hold depression in our hand. But what we can do is that we can assess items. We can gather data based on items that we believe are caused by depression or indicative of depression. So, if you have the CESD, there's somatic symptoms, changes in sleep, changes in appetite. There's mood symptoms, feeling sad or losing interest. There's cognitive symptoms. So all of those 20 items that are traditionally measured are believed to represent depression, and we can measure those directly. We can get data on those indicators of depression directly. And so that's what we're trying to do by using latent variables. All right, so latent variables have again, several important properties. One, it increases our statistical power and provides more accurate parameter estimates, but also it measures our variables of interest at the level in which we believe they occur, when we aren't necessarily doing that when we are using sum scores. All right, so in lavaan, we're going to name our four variables, four latent variables. We're going to have our predictor be dyadic coping for men and for women. So if you see the M, it's for males, and if you see the F, it's for females. I probably need to change this because a lot of times you have mother and father, and that can get really, really confusing. But again, our sample is on heterosexual couples, so they are theoretically distinguishable. So we're going to use male and female. And so we use the equal tilde sign to represent factor loading. And then we have 5 items on the dyadic coping subscale for both men and for women. And then on the CSI, the couple satisfaction index, we have 4 indicators for men and women as well. So you will notice that on the CSI, we have items 1, 2, 3, and 4. But I have item 2 as kind of that first loading. So the reason I do that, and I do it very intentionally, is because the default in lavaan and M plus and most SEM softwares is it's going to be the marker method within confirmatory factor analysis, within latent variable modeling. And what the marker method does is it fixes the loading of this first item to be 1. And what that does is it sets the scale for the latent variable, for this variable here, right? Because a latent variable, it's unseen. It is not in our data set. That is one of, I believe, Ken Boland kind of gives a very general description of what a latent variable is. It's anything that you believe exists but isn't in your data set, right? And so because it doesn't exist in our data set, we need to pin it down in some way. We need to know how to scale it, how to measure it. So we need to give it a mean and we need to give it a variance. Well, using the marker method, we are setting the scale of the latent variable's variance through this first indicator. So essentially, all of that information that indicator is kind of holding is kind of pushed up into the latent space. All right, so you can think about all of the variance that this first item has by setting that loading to 1, and technically you don't really see it here, and we're not really going to go over it, but you would fix the intercept of that first variable to be 0. You're pushing all of that information up into the latent space. And so now we have a reference point for the latent variable's mean and the variance, and it's coming from that first variable. And so in previous work and in preparing this, I tested measurement and variance as one should for all of their analyses, and found out that this item, CSI1 for males and females, is not invariant. So we only have partial invariance with the CSI in this data set. So what that means is if I use this first variable to set the scale for relationship quality, the CSI for men and for women, and it's non-invariant, that means the variances of the latent variables are actually going to be different for men and for women, and they're not going to be comparable because that first item is functioning differently between genders. So again, this is also called differential item functioning. All right. And so we don't want that, because that means we essentially have 2 different rulers by which we're measuring relationship quality. One side's using inches, one side's using centimeters, and that means we can't really compare them. All right. So this is going to be really, really important to have a non-invariant item with your loading and with your intercept if you're doing mean modeling, like a curve of factors process or a growth process. And so that is why you will see that I have this loading, or this item, I should say, fixed to be that first loading, because I have tested the loadings of this item, and it is invariant across gender. So our latent variables are now on the exact same scale, right? So what we're going to do next is you predict our dependent variable, which is couple satisfaction index for male and for females, and that is predicted by an actor effect here and a partner effect here. So actor effect, female reports of relationship quality is predicted by female reports of dyadic coping, and an actor effect, female reports of relationship quality being predicted by male dyadic coping, partner effect. And we have the exact same thing down here, but kind of switched. All right. So male relationship quality predicted by male dyadic coping, actor effect, and female dyadic coping, that's a partner effect. Right. So what you'll see is I just copied and pasted from above. What you could also do if you rather organize your output by actor and partner effects, you could do something like this, where you do tilde. And so we'll say we just want actor effects first. So that makes things a little bit easier. So then we'll do that, but then we'll do diacop men plus diad cop female. So this would be the actor effect, this first one and this first one, and these would be the partner effects, this first one and this first one. Ultimately, it does not matter. It's really whatever kind of coding system kind of suits you or is your preference. I tend to go for this coding system because it's easier. A lot of the times I'm running nested models, so I can just copy the entire syntax into the next model and just make whatever changes I need to. But it is more than fine to do it this way as well. And then we're also going to correlate our latent factors. So male relationship quality is going to be correlated with female relationship quality. All right, so this is going to be, again, a covariance. And then we do the same thing for dyadic coping. So 1 tilde is regression, 2 tildes is variance or covariance. All right. And then because we have dyads and because they are interdependent, we are going to need to correlate the residuals. So what we do is for each item, we create a residual covariance across gender. So for the first item on the common dyadic coping subscale, which is item 31 in the overall DCI, we're going to correlate male and female reports. So male has an underscore M for the observed variables, female does not. And so what that is essentially saying is that there might be an unmeasured common cause of something that's influencing men and women to report similarly or perhaps even differently on this specific item. And so this is actually really, really important and why you shouldn't do like a multiple group invariance test is because you're actually not able to specify these residual correlations and you're not accurately representing the non-independence of your data if you were doing like a multiple group model, for example, when testing measurement invariance, right? And so we're going to do that for all 5 items here, and we're going to do this for all 4 items here. So next, we're going to create our fit object. And so this is going to be I just call it fit dot whatever my model is called up here. And we're going to use the sem function. This is our model up here. So it's going to be estimating all of this good stuff in green text. We have our data. We are going to be using robust maximum likelihood because relationship quality / relationship satisfaction tends to be a highly skewed and kurtotic variable. So to address that non-normality, we are going to be using maximum likelihood with robust standard errors, which goes in and kind of after the fact, adjust your standard errors to be more accurate, as well as adjusting your chi-square statistic. we have a little bit of missing data here. It's not too bad, but we are going to specify full information of maximum likelihood to estimate those missing values. Mean structure equals true. We actually technically don't need this, but I kind of do this kind of just by default. Same thing with std.lv, standardizing your latent variables. Again, we probably don't need that, and actually we can probably take it out. Um, we also want a summary of our results. So if you just enter this in and you hit enter, you will see nothing pop up because you told lavaan to estimate it, which it did. You will probably see a change in your environment. You see my environment's actually pretty busy through other projects, but you will see your fit.latent APIM kind of pop up, but you're not going to see anything down here in your console. All right, so that's why you need the summary syntax or the summary function. So you're going to specify your fit object. You're going to specify the fit measures. I believe by default, lavaan gives you your chi-square test and maybe the SRMR, but it will not give you your CFI, TLI, RMSEA. So that's what fit.measures is going to give you. We want standardized values, and we want to know our R squared or explained variance. This would be quite uncommon, but I'm actually a huge proponent of the residual correlation or covariance matrix. What we actually find is that fit measures like the CFI, the TLI, and RMSEA, they tend to not be sensitive to all model misspecifications. They're generally going to pick up on, substantial misspecifications. If you have a good model, let's say it's a CFI of 0.99, and you make a change and you remove a path that really shouldn't be removed, your CFI is going to go down to 0.94. And there's a substantial change where you say, "Whoops, that's probably not a good thing." But if it's a significant path, but it's something that's more nuanced, perhaps the regression coefficient is p equals 0.04. Your CFI might not always pick up that difference. Your RMSEA might not always pick up that difference, and we would conclude that we have a correctly specified model when we really don't. And so what I like to do to combat that in a way by supplementing the information that we have is by looking at the residual correlation matrix. And so what the residual correlation matrix does is it examines, what is the model estimated association between the variables, like what does the model expect? And once the model has been run, what values actually occur? And so what we can do is we can subtract those values from one another to obtain kind of an indicator of whether or not certain parameters, means, regression coefficients, variances are over or underestimated. And this is kind of more along the lines of kind of local misfit. And again, I'm a much bigger proponent of local misfit because again, global misfit, it just doesn't do a very good job in my eyes. And there's a lot of flaws, a lot of problems, and it doesn't really give you any actionable intel on where there is a potential problem, whereas your local misfit absolutely does. So what we do is we use lav residuals, the function within lavaan. We type in our fit object. Type equals core will provide standardized or correlation, residual correlations. I want my standard errors. And then I'm also going to request a z statistic. So once you subtract your model estimated versus your model implied correlations from one another, you can actually throw a z-score on that to see if that difference is significantly different from zero. All right. And so that is what we are doing here. Actually, let's go into this summary. We'll make that true just so you can see all of the information. I want a summary table. I want outputs. I want this in a list form. And then I want to add the labels in the output. And I'll also request modification indices, right? So this is, again, another This is what modification indices are, is they're kind of getting at local misfit, but they're doing it at a very atheoretical manner. They are just throwing every possible change that you can make to your model that would improve your chi-square, and giving it to you and allowing you to make the choice. So you should not follow modification indices blindly. In fact, there's been studies that have intentionally created a misspecified model, and never do you actually get back to the correct population level model simply by following modification indices. You should always use theory. You should always look at other statistics. You should always be tracking the associations across different models, the regression coefficients, covariances, and things like that to make informed decisions. So that is the basic syntax for the latent variable APIM. All right, so we can go ahead and we can run this. All right, so you'll see here's our output, but since it's kind of messy in our markdown, we can just go ahead and look at it in the console. So here is our model data fit in terms of the chi-square. So you can actually see this would be your maximum likelihood estimate for your chi-square statistic. And here is your chi-square statistic accounting for the scaling correction factor. So you can see our chi-square goes down by, 16, 17% by using robust maximum likelihood, which again will only serve to improve model data fit as well as our standard errors. So our CFI and our TLI they're okay. They're not really anything to brag about. 0.95, I guess 0.96 if you went around, 0.94. So okay, but again, I'm not saying this is the best model ever and there's no misspecifications here. I'm saying maybe there's a little something funky going on. I'm probably feeling okay, but I might poke around, and just to foreshadow a little bit, there are some problems within this model that our CFI is not really picking up with blaring red lights. It's kind of illuminating something's there, but it's not actually picking up on kind of what the actual problem is. Our RMSCA is doing okay. Our CI is actually pretty tight. Our our upper bound is within the range of what is acceptable. Oftentimes it's 0.05, 0.06, or 0.08, depending on kind of who you are. So again, generally we would be okay within most folks and how they evaluate it. And our SRMR is fine. You generally want this to be, again, below 0.05. But again, fit statistics vary widely based on the type of model that is being run. An observed variable path analysis versus like a confirmatory factor analysis. So we will scroll down, and we'll take a look at our kind of our confirmatory factor analysis, our kind of our measurement model in a way. So we kind of see that our factor loadings are generally pretty good. So 809, 70, and then these are dipping a little bit below kind of where we want. So this is signaling that there's something a little different about these two items than there is compared to the other three items. And we see the same pattern for males, where these factor loadings are 0.70 and above, and then these other two are below 0.60. And then we have the exact same thing happening over with the females. So what we can see also here is that we have pretty good factor loadings for relationship quality between males and females. Again, we still have this one kind of fuddy-duddy item that's not performing particularly well, but ultimately it's going to not really be an issue because we can have partial invariance as long as we have this first indicator really being solid among both groups, both across men and women, then we're going to be fine. All right. So we can move on. We can, even though we have our actor and our partner effects here, we're going to completely ignore them for right now because we need to ensure that we actually have a strong kind of measurement model. All right. So we'll begin to scroll down. We'll scroll down some more. R squareds, covariances. We're not all that interested in things like that at this point. So what we are going to do is go to the residual covariance matrix. All right, so here we have our residual correlation matrix. It says cove up here, so which generally means covariance. But if you recall in the syntax, I typed in type equals core. I'll actually scroll up and I can show you where I did that. We'll do it here. So type equals core. Okay, so that means standardized correlation. So uh, here, these are all correlations. And so a positive value indicates that a parameter is going to be overestimated, and a negative value indicates that that parameter is underestimated. So your diagonal values are going to be your variances, and your off diagonal are going to be your covariances or your correlations. And so, as you know from a correlation matrix, if you've ever kind of written up a paper, the diagonal values are almost always either dashed, either they're zero or they're one, or sometimes you'll see a variance estimate. But here, um, uh, it is zero because there isn't because it's we did type equals correlation again, which is in a standardized metric. If we did type equals covariance, we would get variance estimates on these diagonal elements. So what we're really looking for is actually we'll scroll down first to things that are happening down below and then come back. We want to look at the z-scores. Right. So what that is it's going to be you have your correlation matrix up here, then you have your standard error matrix right here. So you have a standard error for each parameter value, and then you compute your z-score from those values. And so if you recall from Stat 101, your critical value for your z-score is 0.196. And so any value above 0.196 means that it's significant. But because models, especially latent variable models, are sensitive to sample size, number of parameters, the extent to which our observed variables and our latent variables associate with one another, all of those things can influence the z statistic. And so I'm not going to look at, z equals, right here, negative point 2 or 2.0, sorry, and say, uh-oh, our model is wrong because of that. Again, these are going to be highly sensitive. So I'm really generally looking for patterns here. So I'm looking, are there certain items that are consistently getting high z-scores? Could that be a problem? Or is there an outlier? Is there one of these things is not quite like the other in terms of z-scores? Right. So those are the kind of the patterns I'm looking for. So here, I'm not really seeing kind of a whole lot looking down to this first column. This is a little higher than the others, but it's not really bothering me too much. Everything in this one's non-significant. Um, this one's a little funky. All right, that one's kind of beginning to get a little bit further out. This one's kind of small. This one's kind of small. Nothing here kind of is worrisome. Again, small, relatively small, relatively small. But then here we're starting to get a little bit bigger. So this negative 3.62 is a little bit more problematic. And same thing with this negative 2.43. So we have kind of two outlying values on the same item, and they're outlying on item 34 and 35. So that there might be something there. So that's something I'm kind of tracking. Nothing here really. And the rest of these look really pretty solid. All right. And then we have the rest of them down here. Um, so there's a little bit of concern, but nothing that's screaming, okay, we have this massive problem. And honestly, I would rather have a massive problem than kind of some of these types of scores right here, because that's massive problems are actually easier to detect and they're easier to address because oftentimes it's going to be like a model misspecification. That's easy to fix. Whereas if you have kind of chronic low, medium amount of misfits across your entire model, that can be difficult to detect, and it actually can have pretty profound consequences. So again, that's why I look for patterns. And so what I'm sensing here is that it's item, 35 is acting a little funky for women. So it's got one here, it's got two bigger ones here. It's got another one here. It's not behaving kind of all that well. Same thing with item 34. It's kind of got some more consistent, associations with or under and overestimation with other items across dyad member. So I'm gonna look into that. All right. So what I'm gonna do now is before making any kind of modifications to this, um, and actually here we can look at modification indices. So it's saying after looking at the residual matrix, correlate item 34 and 35, and that'll reduce your chi-square by 15. So that makes some sense. Uh, this would indicate cross-loading across construct, and same thing here. So those make less theoretical sense. So I'm kind of leaning towards investigating this. So what I'm going to do is rather than just throwing this covariance on there, I'm actually going to take a look at the dyadic coping inventory, my actual measure. So here are the items that we use, these 31 through 35. And we have kind of stress communication, we have stress communication, we have kind of stress communication. But here, it's kind of feels like there's like an aspect of like physical intimacy. There's an aspect of like distraction from problems. It's other things that you might be doing. And so so the low loadings are actually kind of making a little bit of sense to me now that these first three items are very communication based, right? These other two are much more kind of like other forms of behavior based. So maybe the reason we're seeing some of those over and under estimates is because there needs to be a residual covariance here. All right. So what we're going to do is we're actually going to go and we're going to add that into the model. All right. So that's what this model is. So this will be model. This is our second model, latent APIM 1. And so all I did is I copied the exact syntax from above, and the only thing I changed is I covaried item 34 and 35 for men and for women. So I only correlated men's residual covariances together, or residuals with a covariance together, and I only correlated women's. So together. So I did not correlate, women's item 34 with men's item 35. Right. So I only did it within person. Right. And so what we're going to do is we're going to run this, and we're going to see to what extent did that help our model. All right, so we'll go ahead and open this up, and we'll scroll up. All right, so before our previous model had 120 degrees of freedom, we added two parameters, so that means we are down to 118 degrees of freedom. Again, a nice way to kind of check that we have the correct model and our syntax is error-free. So we can kind of begin to take a gander. We can see our CFI and our TLI both went up, so we're moving in the right direction. Our RMSEA, I think it went down a little bit from what I recall. I think it was a little bit over 0.05, or actually maybe even 0.06. Um, and our 90% CI is now completely below 0.06, whereas before it was like 0.062 or 0.064 or something to that effect. All right, our SRMR went down by 0.002. So there's clearly some benefit in the model as shown by our global fit statistics. We'll see there's a little bit of change that's happened in the factor loadings. Not too much, but we do see that the factor loading for DCI 35 actually went down somewhat substantially. And now the factor of DCI for females is only accounting for 25% of the variance in this item, right? So that's potentially problematic from like a construct validity perspective that this item doesn't seem to be behaving in a well-mannered way. All right, so that's something again to keep an eye on. So again, we're still going to ignore actor and partner effects. They're still not relevant, but we are going to go back down to the residual matrix and begin to see what is happening. Actually, one thing I forgot to do in the previous model is I told you we would go back up and look at the correlations, um, which we didn't do. So just because something's significant doesn't mean it's practically important. Because again, you can have actually a really small correlation and you can have a really small standard error, and that would actually come up significant. So you're detecting a difference, but that difference isn't practically meaningful. So an example of that would be your residual correlation is point oh point oh five, but your standard error is 0.001. And so when you divide those two together, you get a test statistic that's really, really significant. But the magnitude of difference between the two models, that 0.05, might not be all that meaningful, especially if you have a model that's explaining a lot of variation. So again, it's a gestalt approach. But when I see that DCI 34 and 35, that covariance is overestimated by 0.18, that is huge. That is a massive misspecification. We have something down here that's saying exactly the same thing. So this is really what's kind of clued me into, okay, these two items are potentially problematic. Again, right here, DCI, 35 has a massive overestimation of that association with CSI 1. So again, I'm beginning to see a pattern where a lot of the problems that we're seeing is potentially due to these two items from both a theoretical perspective as well as an empirical perspective. So we'll scroll back down to our now updated model, and we will check back in with those residual covariances. And this went down by half, so that's good. But we still have some problems here. We have more problems that are popping up here. So when we've created those residual correlations, other things have shifted in the model because SEM is a systems of equations based approach. So you tinker around in one aspect of your model, there's going to be ripple effects to all other aspects of your model. It's like throwing a stone into a pond. You throw it in there, you can kind of see the waves, gradually fan out, and eventually they get smaller and smaller and smaller. Where the further away let's say the leaf that you're looking at, the less it goes up and down based on those ripple effects that were created by a rock. But one of the things that we have to be cognizant of is how big of a rock are we throwing? Are we throwing a tiny little pebble that's going to create small little ripples? Are we throwing a big honking boulder in there, and that's going to create these massive waves throughout the entire pond? And so what we're doing here is kind of evaluating that, and we got problems, major problems with all of these really high residuals. The same thing here with DCI 35, another one right here. So another thing that we could do is that we can actually create a residual covariance between item 34 and 35 across gender. So that would mean that we're correlating this item in men with this item in women. There might be some unexplained reason that's not in our model why men and women might be related on these two behaviors, these two aspects of dyadic coping. It might be that their general disposition in their relationship is they're very affectionate with one another. So they would potentially engage in, physical intimacy if they were fighting and were trying to deal with a problem, or if they were just kind of just they didn't weren't dealing with any kind of stressors, they would engage in this behavior. So that would be an unmeasured kind of common cause, and a rationale or a potential rationale for including a residual covariance. So that's what we're going to do in this next model. And then we're going to, again, come back and check to see um, the effects um, on the overall model and those residual covariances. So everything, I just copied and pasted the previous model, and the only thing I added is these two lines of syntax. All right. And so I correlated 34 with 35 across partner. So male 34 with female 35, female 34 with male 35. All right. And so you'll notice this is called APIM.1, and you'll notice that I forgot to, somewhat intentionally, somewhat unintentionally, forgot to change the all the numbers. And so if I actually had run this, I would have gotten the identical output from the previous model, right? So, uh, yeah, so we'll change that and we'll get uh, the correct model, and we'll go ahead and we'll take a look. All right. All right, so now we have 116. All right, so now 116 degrees of freedom because we imposed two additional residual covariances. So that means our syntax is correct. And our CFI went up by a decent amount, by 1.3, if my memory is correct, or 1.2. TLI went up. Our MSCA went down a skosh. Our confidence interval got a little bit tighter. Our SRMR has been kind of hovering around 0.04. So again, we're doing generally a pretty good job with model data fit. It's getting better and better, the more we're tinkering around with it, which means we're probably in the right direction. All right, so we'll scroll down and look at the residual matrix, and we still got problems. So DCI 34 is still problematic. We got another one right here that's still not cooperating. And so again, these items, again, theoretically and statistically, they don't make a kind of a whole lot of sense. That they're kind of wrecking havoc when we fix something in one part of the model. Right here, now these residuals look really, really good. They're popping up somewhere else in the model. We're playing a game of whack-a-mole right now where you hit this mole down in one part of the model and it just pops up in some other part of the model, which means we actually have a general misspecification within the model. Something is fundamentally wrong with our model and we need to determine what it is. But one of the good things, because that can be really, really challenging for a lot of folks in a lot of different models, is we kind of see it. We've seen a pattern, right? We've seen item 34 and 35 be really, really consistent across all models in terms of that model misspecification. So how it's showing up is a little bit different, but it's always those same two items. And so what we're going to do next is we're just going to address that by dropping those items. But before we do, I want to specifically go into how do we know that the models are statistically one is better than the other? And so normally you would do a chi-square difference test, you would do a likelihood ratio test, and that's what we're going to do, but it has to be in a modified version. Because we are using robust maximum likelihood, we are implementing a scaling correction factor or the extent to which we go in after the party we clean up all of the beer cans by estimating how much of a problem is the non-normality in our chi-square and in our standard errors. And so we do that by doing a scaled difference test. So there's actually a package in lavaan, or within R, I should say, SBS diff, and it's a incredibly simple package. All you do is you put in these values and use, so it's chi-square of your more complex model with your simplified model, or your simple model versus your more complex model. You put in your degrees of freedom for both models, and you put in your scaling correction factor. That's what the C0 and the C1 is, right? So this our more complex model has fewer degrees of freedom, all right? And so what we'll do is you just enter these in, and these are available kind of in your output. So all I did was is pull them from here. I put in this, I put in this, I put in this, and that is all I need. And I did that from both models. So I'll scroll up to the previous model and show you where I got that information. Exact same place, right? So right here, and right here, right? So we'll minimize this. And what we'll do is we can go ahead and run this. And this gives us a chi-square difference test. All right. And so what this does is it evaluates whether or not our model is harmed or not. And it turns out by by not including these residual covariances, our model is actually significantly worse. It fits significantly worse. So what that's saying is we need these residual covariances in this model because it significantly improves the extent to which we are reproducing our observed data. All right. So we actually did that technically after both. And so I didn't necessarily go over it after that first time, but we do this test twice. Every time we change the model, we're going to do a likelihood ratio test to do that. The one thing I will say about this is when you use this package, you'll notice in your environment that the values um, are specified, and because I am telling lavaan that these are the values, and so they are going to be transported over here into your environment. They're going to be the exact values that you specify. But what happens is if you use this package multiple times, you will be doing multiple likelihood ratio tests. And so if I go up and I just run this, it's coming out with the exact test statistic as below. That's because the values haven't changed, all right, in my environment within lavaan. My chi-square is still 183, but in this model, it's actually 200. All right. So this was again, comparing the first to the second model, and then this is comparing the second to the third. And so what I need to do is I need to go in and I actually need to just rerun this. We'll go in and do that. So now my chi-square values have changed. You see that? They're now the correct values. And so now I can go in and run this and I get the correct chi-square difference test. All right. So if you're getting the same result over and over again, it's because you actually need to go in and tell lavaan that the values are different for your different models. All right. So the last thing that we are going to do is just drop those two dreaded items. We're going to go ahead and just estimate dyadic coping with these three items, 31 through 33. So one of the benefits is that we are potentially getting a more kind of homogeneous construct. We're assessing more of the exact same thing. We have better construct validity. But One of the problems is because this is coming from a standardized scale, our results are no longer directly comparable to other results that are using this exact same subscale in these analyses. So again, there's a trade-off here. Perhaps we get better validity, perhaps we kind of isolate what we actually want to isolate, but also it also makes our study not necessarily directly comparable. So we have to, again, have to weigh the pros and the cons. And sometimes there are just cons, as in if you're using a certain scales, their manual will say that you have to use the scale in this exact manner and you are not allowed to modify it. So again, you just need to be, again, cognizant of those types of things. But for here and for right now, we are going to assume that we're allowed to modify the scale. We're just going to only analyze those three items and we are going to drop them. So again, I've copied and pasted everything from above, but I've eliminated those residual covariances that were down here. And I've eliminated those two items from the dyadic coping inventory. All right. And so again, we need to be careful, APIM2, so we actually need to change this to APIM3. Otherwise, again, we're going to get the exact same results and we are just going to confuse ourselves and it will take us far too long to realize what our stake is. Whoops, I even changed it in the exact wrong place, even though that, ultimately that would have been fine. Oh, I already did that. So, see, that's this, you live and you die by the copy and the paste within lavaan, and I tend to live and die very strongly by the copy and the paste. So we'll go ahead and we'll run our model. And so we, again, here's our chi-square for modification indices, but we'll kind of look at that first. You can ignore this warning. You don't need to worry much about it. So we lost quite a few degrees of freedom, but look at our model data fit now. Especially with that scale correction factor, our p-value is actually not significant, which means that even a highly, highly, highly sensitive test of the chi-square is saying we actually have a good fitting model. It's rejecting we failed to reject that null hypothesis that our model isn't good fitting. So again, really good spot. Our CFI and our TLI are looking beautiful. Our RMSCA is looking really, really good. Our SRMR dropped by 25%. So we're looking really nice. All right. Our factor loadings are all about the same. We would expect these to change just a little bit. This is perhaps a little lower than we want, but again, it's not outrageously low and it didn't change all that much. Uh, this couple satisfaction index, that's not changing hardly at all. But what we can see, whoops, I think I may have actually gotten ahead of myself. I think I may have actually run, yep, I did. I actually ran the wrong model. So we're just gonna go ahead and hit _2. That's the next model we are going to run. That's when we are going to compare the actor and the partner effects or within dyad moderation. So again, my apologies for any confusion. But again, same thing, same idea. Significant or non-significant. So we have a really good fitting model, 994, 992, 0.023, 0.025. We're living large here. Again, factor loadings are looking really, really good on average and in general. But really the test that we want to see or the change that we want to see is in this residual matrix. And so we'll scroll down and we kind of see that there's no outlying values, really. We have one that's marginally significant, but other than that, everything else is below our z-score. So we're fitting the model, we're replicating the data really, really closely. And we can verify that by looking at again, kind of the effect size of how big the residual correlations are. And again, for the most part, they're looking really quite good. This one's again getting a little high, and that will, impact the parameter estimates in every way that you can get from CSI 2 from males to DCI 33 for males. Um, or 32 for males, sorry, excuse me. But that's really gonna show up in your factor variance or factor covariant, your covariance between the two factors, or your regression coefficient in our example. And that's not gonna, it doesn't look like that'll be kind of a major problem. That any potential misspecification will get kind of spread out, and it won't likely cause any major problems in the long term. Right. So again, all of this is looking really, really good. And so it's again building evidence that it's those two items on the dyadic coping inventory that are causing problems. So now what we'll do, because we now feel good about our measurement model, then we can go estimate our actual actor partner interdependence model. And we can actually begin to interpret the results. All right, so that means this model that we just ran, we can now go and take a look at these guys, these regression coefficients. All right, so we have a really strong actor effect for females, 0.75 for a standardized regression weight. We do not have a partner effect, so male dyadic coping does not predict female relationship quality. But for men, we actually have kind of an opposite pattern of effects, where the female's partner effect is actually really quite strong, and it's highly significant. And we also have the male actor effect is also significant, but to a much less extent compared to the female. And so what we have here is that female relationship quality is determined by how much females, I guess how high they score on dyadic coping. And there's a really, really strong relationship there. But male relationship quality, or how happy men are in their relationship, is determined not only by their own score, but also their partner score on dyadic coping. All right, so you can actually empirically test this using dyadic patterns and estimating the K parameter. We're not necessarily going to go through that in this video, but to just as a teaser, the male results would be more of a couple-oriented pattern where the ratio of the partner to actor effects is equal, and we have an actor-oriented pattern for females where the actor effect is significantly stronger than the partner effect. All right. So now that we've kind of seen this and we're kind of, digesting the results, we're noticing that this is way larger, that actor effect, than this. And we see that this partner effect is way larger than this one. So what we can do is we can now compare them, and this is testing moderation. This is specifically testing within dyad moderation. And you'll probably say, if you're familiar with the APIM, I've kind of heard about this before. This seems familiar. Where am I kind of why is this, why am I getting this idea? Why have I heard this before? And this is actually kind of a modified version of the ISAT model, where in the ISAT model, we're constraining the means, the variances, and the covariances to be equal across gender. And a significant test means that they're empirically distinguishable. Whereas here, we're only constraining the actor effects. All right. So it's still testing moderation. It's just a very specific form of moderation. All right, so we'll go ahead and we'll do that. And you kind of already know kind of where this is going since I had inadvertently skipped ahead a model. Everything here is exactly the same as the previous model, except I've added in the A1 times the star for the two actor effects. And what this will do is a 1 degree of freedom chi-square difference test. which I didn't calculate, but essentially you would just go, as we did up here, you would just run this again and just enter in the values for um, the um, the nested models, and you could see whether or not imposing this constraint is going to significantly harm the model. And if it does significantly harm the model, then you have moderation by gender. So we'll go ahead and we'll run this, and you can ignore that warning sign. Um, so what we didn't actually go ahead and run the test, but I have run the test before, and it is significant. All right. So the difference in the chi-square is going to be significantly different, which means imposing this constraint of the actor and the two actor effects to be equal actually harms the model. Because again, there was this massive difference between the effect size of those regression coefficients. And so here, technically, you want to look at only the unstandardized effects because although we have a non-invariant factor loading to set the scale for relationship quality and dyadic coping, those factor loadings are going to be slightly different across men and women. And so when you standardize them, you're actually going to be dividing by the standard deviation, which is an extension of the variance. And if they have slightly different variances because the standardized factor loadings are slightly different, then technically you can't really trust the results. And indeed, you see a very minor difference. But with the unstandardized effects, you will always get the exact same factor loadings here. So, or parameter estimates, I should say, regression coefficients. So you would always want to use the unstandardized to be perfectly clear or get the perfect kind of result. Whereas then if you compare standardized estimates, you're probably not going to run into many problems. And if you do, you have measurement problems, and there's many other things that you need to be doing. All right, so that's one test. So now, actually, let's minimize this. Now let's do the partner effects. So I copied and pasted the syntax, and I removed the A1 that was here. That was there in, oops, that was there in the previous model. Right, so you see up here. So that was right here. I removed that. And by removing those effects, that means it's freely estimated because this P1 star across both means every value with that label in front of it will be constrained to equality. So now we're going to run the partner effects, constrain them to be equal. And again, we didn't technically run the chi-square difference test, but I will tell you it is significant. All right. And so, whoops, I think here we go. What I did was is actually this is perfect. Perfect um, perfect way to show you about the potential problems. Even though up here I specified the APIM 4, down here I did not change the 3 to a 4. So the result I actually got for the APIM are identical to the previous results. Remember, this was our p-value. So I ran this model, but I only got the output in the fit statistics for our previous model. So again, the dangers of copying and pasting you are seeing live. Again, some of these are intentional and some of these are unintentional. So we run it again, and we're going to get different results this time. There we go. That's a different p-value, same number of degrees of freedom, but our chi-square is going to be different. And if you run the calculations, then there is a significant, the model is significantly harmed by by imposing this constraint, which means we have gender moderating the effect of of the partner effects, where for the actor effects, women's actor effects were significantly greater than men's, and in the prediction of male and female relationship quality. And in this model, we also have the female partner effect being significantly greater than the male partner effect. All right. So we'll scroll down and we can actually take a look at that. Take a look at these regression coefficients, right? So they're constrained to be equal, and that significantly harms the model. If you remember before, this was, 0.056, and this was zero point 0 or 0.33 or something like that, or 35, something to that effect. So when you kind of essentially kind of take a not really, it's not exactly a dyadic average, but it's kind of like a dyadic average when you account for missing data, equal sample sizes, and things like that. You can kind of think of it that way, that it actually harms the model. So that means that we need to free up those parameters, and we go back to our model 2, where we don't have those constraints in the model. And this is what we would write up after adding in our covariates and things of that nature. And then we would talk about constraining the paths to equality and things of that nature. All right. So hopefully this has been as insightful in using several different packages within lavaan, understanding the latent variable actor-partner interdependence model, and seeing kind of the complexity that you will kind of inevitably encounter when you are using latent variables that you don't necessarily encounter with observed variables. It gets really, really complex really, really quickly. And so again, it's something to be mindful of and be really cognizant of knowing the things that you're measuring and ensuring that you're actually measuring the exact same things across dyad members. Hopefully this has been helpful, and thanks so much for watching.